Welcome everyone. Today I want to talk about a very interesting shape, one that has an infinite perimeter yet a finite area. You may have heard these shapes referred to as fractals, and this particular fractal is called Koch Snowflake, and it is one of the earliest fractals described by a Swedish mathematician way back in 1903. So the process is really simple. You start with an equilateral triangle, then you divide each side into three pieces. Then, taking the middle side, you construct another equilateral triangle with those lengths pointing outward. And finally, you remove this middle piece to make a closed shape. And you get these kind of spikes pointing outwards from the middle of these sides. And so what is interesting is that if you repeat this process indefinitely, the perimeter will diverge to infinite length, while the area will converge to a finite number. And today I will explain to you why this is true. We are interested in four characteristics of the shape, namely the side length, then the number of sides, so then we can find the perimeter, and also the area. And really, Koch snowflake, you can think about it as the limit of a sequence of shapes. So those four characteristics we can also describe as a sequence. So for example, we can do the side length. First, we need an initial side length, which I will call L of 0, and that just depends on our choice. We can choose it to be anything we want, but I think for simplicity, if we let it be equal to 1, that will be pretty easy. We can then scale accordingly if we want to. So let the first side length of our first equilateral triangle be 1. And so we want to find the side length of the nth iteration. Well, it's really quite simple. We can describe it recursively and better explicitly. The nth side length, well, you just take the previous side length and divided by 3, as I described here in the process in the beginning. So L of n equals L of n minus 1, and this recursive relation can be satisfied also explicitly. So L of n will be 1/3 to the n. We're just repeatedly dividing and dividing by 3. So this is quite simple. Now, for the number of sides, we also have an initial number of sides. I'll call S of 0. It's equal to, of course, 3, number of sides in the triangle. And now notice what happens to our sides as we go up. So in our process, we first split each side into 3 parts. So here we have our 3 parts. Then we construct a new triangle by adding 2 parts, and then we remove the middle one. So really, after addition and subtraction, we are left with 4 new sides. So our explicit formula will simply be 4, our initial times 4 to the n. We started with 3, and every iteration we are multiplying by 4. So at each new side, we are adding 4. And so this will be the relation. Now we can very easily find the perimeter, because the perimeter is simply the number of sides times their length. And that's because all of their lengths are the same. And using these formulas that we found, we can find a formula for the perimeter, which I'll call P of n, which is L of n times S of n, which is simply 3 times 1/3 the n times 4 to the n, and by powers of exponents, this becomes 3 times 4/3 to the n, simply merging these into 1. And so we found our perimeter. Now the area is the trickiest. Let us write down on A0 the area of the first equilateral triangle. How can we do that? Well, we can use a formula from geometry, which is half times the side lengths around a certain angle, where the side lengths are squared, and we take the sine of that angle. So this is going to 1/2 times 1 squared times sine of 60 degrees, which is of course root 3 over 2, paired with the 1/2. This becomes root 3 over 4. So how can we find A of n? Well, maybe take a look at A1 first, the first shape, or not the first, the second, we're starting with 0, A1 in here. Well, clearly we have our first equilateral triangle contained in that shape. It is right here. And we are also adding 3 more triangles to the sides around it. Well, notice, how many triangles are there? There are as many triangles as the number of sides in the previous iteration. And also, to find the areas of those triangles, we have to use the length, the side length of the iteration that we are on. So clearly there's something interesting going on here about the previous iteration and the iteration currently. And in fact, if we keep going, if we go to A2, notice we'll have to compute new triangle areas because we're adding on to the shape. And there will be as many triangles as there are the number of sides in the previous iteration, and we will use the length of the current iteration to compute those areas. So let's try to write out A of n as this sum of areas. A of n, we're going to clearly start with a 0, which is going to be root 3 over 4. Then we're going to add the area of the three triangles around the sides of the quadrilateral triangle that we just counted into it. So what's going to happen, there's going to be S0 of them, so the previous iteration of number of sides. And then to find their area, we're going to use the new length 1, square it, and then multiply it by this coefficient that is 1/2 the sine of 60 degrees because it is an equilateral triangle. So it is going to look like this. This is going to be a 1. Now to add a 2, I hope you can see the pattern. We're again going to take the number of sides in S1, like this, and then to find the areas of each of those triangles, we're going to multiply it by, the areas will be L2 squared times the coefficient root 3 over 4. And so we continue summing this up until a certain n, and we're going to do this until a certain L. Because here it's L0, then L1, then L2, they each correspond to the figure that we are on, that we are counting the area for. So the number of sides is just about the previous. So we're going to keep adding until it's going to be S of n minus 1 times L of n squared times root 3 over 4. This is going to be A of n. We can write A of n more concisely by first factoring out the coefficient root 3 over 4. So we get, first for the special case of A0, there's going to be a 1 here, and then we can use sigma notation. So starting from 1, I think is the better choice, going to n, we have L of I squared, and then times S of I minus 1. So the current iteration, of which is the length, and the previous iteration for the number of sides. And so this is our expression for A of n. Now we can answer the main question of today's video. What is the limit as n approaches infinity of P of n, and that same limit for A of n? So where does the perimeter tend to as we repeat this process indefinitely, and where does the area tend to? It's very interesting. Look at this. The limit as n approaches infinity of P of n, using the formula for P of n, this becomes the limit to infinity of 3 times 4/3 to the n. And ignore the 3 here, the 4/3 to the n. 4/3 is greater than 1, and obviously if you keep raising something greater than 1 to a power indefinitely, it's going to grow without bounds. So this limit just diverges in the positive direction, like that. Now what is the limit of A of n as n approaches infinity? Well, substituting this formula in, we get some interesting things. This becomes the limit as n approaches infinity of this whole formula, root 3 over 4 plus root 3 over 4 times this sum to n of, and what I'm really concerned about here is the L of I and S of I. We can substitute in the formulas that already use n in there. So L of I squared, squaring this, we get 1/9 to the n, and then multiplying it times S of I minus 1, we get here 3 times 4 to the n minus 1. And sorry, it's not n here, it's I. And this becomes 3 times 4 to the I minus 1, like this. And how do we simplify this even further? Well, with a bit of basic algebra, combining stuff, we get root 3 over 4 plus another root 3 over 4 times the sum. We can write it in shorthand as the sum to infinity from the index I. And combining this, we get 4/9 to the I times 3/4. And why? Well, this 4 to the I minus 1, I simply wrote it as 4 to the I over 4, divided by 4, I mean. So you should recognize this series as a geometric one with a starting term 3/4 and a common ratio 4/9. Except it's not really geometric because here our starting index is 1 when it should be 0. But we can still evaluate it using the formula. We can just have to subtract the term when I equals to 0. So here it will be 3/4. And so we get our final answer for this limit of A of n. If I write it all out, it's going to look like this. Root 3 over 4 plus root 3 over 4 times first term over 1 minus the common ratio, but minus 3/4, where is the term for 0. And so this is it. And with a bit more simplification, we can get that this is equal to 2 root 3 over 5, which is indeed a finite number, unlike the perimeter which diverges. How cool is that? So that is it for today's video. Hope you all enjoyed learning about these fractals and how cool it is. Perimeter diverges, but the area converges. And I will see you in the next video.